Hello and welcome back. In this video we'll be discussing infrared spectroscopy, which is the first half of Chapter 14 of Klein Organic Chemistry version 3. So spectroscopy involves an interaction between matter and light itself travels in waves, and those waves are quantized into packets of energy called photons. So light has properties of both wavelength and frequency, where wavelength is inversely proportional to energy and frequency is directly proportional to energy, where E is equal to h nu is equal to hc over lambda. And you probably remember that from general chemistry. So infrared spectroscopy deals with electromagnetic radiation in the infrared region, which is a longer wavelength than visible light and a lower energy or lower frequency than visible light. So different regions of the electromagnetic spectrum are used for different types of spectroscopy, and the different types of spectroscopy give us different information about molecular structure. NMR, or nuclear magnetic resonance, deals with radio waves. IR deals with infrared electromagnetic radiation, and UV-Vis deals with the visible and ultraviolet region. So these give us different pieces of information, and this video will deal only with IR. But even IR, infrared radiation, is quantized, so molecules absorb that infrared radiation only if the radiation corresponds to a frequency that its functional groups can actually absorb. Okay, so a molecule will only rotate or vibrate at certain rates according to the type of radiation or the frequency of radiation that it can actually absorb. So if a photon of light strikes a molecule with the exact amount of energy needed, then in the IR region that will initiate a vibrational excitation. Okay, and so IR light causes molecular vibration, and different types of bonds absorb different frequencies of infrared radiation. Eventually this energy is released from the molecule as heat. So the types of vibrations that we see are stretching vibrations, in-plane bending or scissoring vibrations, and an out-of-plane bending or twisting vibration. So we're going to see all of these types of vibrations in infrared spectroscopy, and so generally we're going to see stretching vibrations in IR. So again, infrared radiation is given off as heat, and that is actually employed in commercial applications such as thermal imaging used to detect, say, where people are located, if woods are being searched for someone who's maybe missing, or even for detecting breast cancer, where because it's been shown that an increase in heat can be indicative of the presence of breast cancer. So that's a new technology where infrared radiation is being employed commercially. So the energy necessary to cause a vibration depends on the type of bond that we have. A carbon-hydrogen bond has a large energy gap, and we're going to see why that is in this video. And a carbon-oxygen bond then has a smaller energy gap. So that energy difference corresponds to that particular wavelength or frequency of radiation that's necessary to excite that type of bond. And frequencies absorbed by the sample can tell us a lot about the bonds that are present, and that gives us information about what types of functional groups are available in that molecule. So our modern spectrophotometers are Fourier transform spectrophotometers, and they'll irradiate a sample with all frequencies of light at one time, and then that light, what they absorb, is then interpreted and transformed into a spectrum. Samples are generally deposited on a salt plate. So there are two hard, solid discs of made out of salt or sodium chloride. Sometimes the sample is ground up in potassium bromide and made into a pellet. The sample is deposited on the plate, either as a pure sample or mixed into some kind of solution, and then the sample is wedged between these two plates and then placed into the spectrometer. Now our modern Fourier transform instrument is a little bit different. The one that we have in our lab actually has a diamond that forms the sample holder, and the sample is placed right on top of that diamond and pressed down onto it. So there are different ways that these spectrometers work, and can depend on the type of spectrometer that you have. So IR is a little bit different from other spectra, from most other spectra, in that we're plotting percent transmittance as a function of frequency. Our frequency is given by wave numbers, and we'll talk about that in just a minute. But our baseline is actually at the top. That's kind of unusual for a spectrum. And then what we're measuring is the amount of light that's actually transmitted or correspondingly absorbed by the sample. So where the light is absorbed, we get a peak where there's less light. Okay, and these peaks are called absorption bands. Notice also that our spectrum goes from about 400 to around 4,000 wave numbers, and wave numbers are given by frequency divided by the speed of light. So the wave number is this little tilde over the frequency sign, and it's given by frequency divided by the speed of light. And the reason that it's done this way is because it translates those numbers into something we can read a little more easily, because the speed of light itself is a large number and frequency is a large number, and so we're going to want to translate that into something a little easier to interpret. So infrared spectra have different characteristics. They have wave number, intensity, which is our percent transmittance here, and shape. And all of those characteristics come together to make the peaks in our spectrum. Now the frequency is determined by this formula here, and we're not going to do these calculations in this class, but this is the formula that actually determines where a functional group will absorb in IR. Okay, and it's dependent upon the bond strength and the mass difference in the atoms. So this formula, wave number here, is equal to 1 divided by 2 times pi times the speed of light times this quantity, F, divided by the reduced mass, where F is the force constant of the bond. So that's a number you can look up in a table. And the reduced mass is equal to the mass of the corresponds to the mass of the atoms by this formula, where M1 is equal to the mass of the first atom, M2 is equal to the mass of the second atom, divided by M1 plus M2. So the stronger the bond, the higher the stretching frequency, and therefore the larger the mass difference, the higher the stretching frequency. Okay, because we're dividing by the reduced mass, and so therefore if we have a larger mass difference, we're going to have a higher frequency. Okay, and also we have this force constant, so the wave number is directly proportional to the force constant, and so if the force constant is higher or a stronger bond, then we're going to have a higher frequency. So what does that lead to? It leads to this effect, which is our carbon-hydrogen bonds are around 3,000 or just below 3,000 for the sp3 hybridized bonds. We're going to see in a minute. Our carbon-deuterium bond, and remember deuterium has a different mass than hydrogen, is going to be at about 2,200. So that reduced mass is going to be different for deuterium than hydrogen. A carbon-oxygen bond is going to be around 1,100. That's a carbon-oxygen single bond. A carbon-chlorine single bond is around 700. A carbon-nitrogen triple bond is around 2,200. Carbon-nitrogen double bond around 1,600. And a carbon-nitrogen single bond around 1,100. So if we consider the regions we're going to see these things in, bonds to hydrogen are between, say, 2,700 and 4,000, and that could be sp3, sp2, sp hybridized bonds. Triple bonds are between 2,100 and 2,300, double bonds between 1,600 and 1,850, and then our single bonds are down here below 1,600, generally in the fingerprint region. So generally, this type of chart isn't very helpful. It's better to study what those features look like in a spectrum in order to understand or be able to predict what type of functional groups you have. Okay, so the region above 1500 is called the diagnostic region, this region here. The peaks in this region are easier to interpret because there's less information in that region generally. Below 1500 we have the fingerprint region where the molecule can exhibit a lot of different peaks depending on the specific molecule that you have. So the fingerprint region, if you have a library of compounds, will give a specific spectrum for that molecule, and you can run your sample against a library of samples in order to determine what your molecule is. Then that fingerprint region is what's used for that. Okay, it's often difficult to analyze, and we don't usually look for a lot of information in that region, but we can get some information from that region. Okay, because the same types of covalent bonds, okay, have similar infrared spectra, we can actually consider the spectra for 2-butanol and 2-propanol where we're not looking at the fingerprint region and they're actually virtually indistinguishable. In other words, the fingerprint region between these two molecules will be different, but the functional groups will give us similar absorptions. Okay, so our OH peak is going to be here, and our sp3 CHs are going to be here. Okay, for both molecules we're going to see a similar spectrum. Now down here in the fingerprint region, they're very different because that's unique to each individual molecule. But these molecules have very similar structures, and that's going to give them, or they have similar functional groups, and that's going to give them a similar spectrum above 1500. So if we consider the stretching frequencies for each of the carbon-hydrogen bonds below, around 2900 we have sp3 hybridized bonds, 3100 we have sp2 hybridized bonds, and 3300 we have sp hybridized CH bonds. So these are our carbon-hydrogen bonds. So the stronger the CH bond, the higher the stretching frequency. So the shorter bonds are going to be stronger, okay, and that's going to give them a higher frequency. Because remember, our wave number is directly proportional to that force constant. So if it's a stronger force constant, it's going to be a higher frequency. So alkyl CH bonds come in just under 3,000, while alkynyl and alkenyl bonds are over 3,000. So if we consider a dividing line just at 3,000, our sp3 CH bonds are just below 3,000. sp2 CHs, if they exist, are just above 3,000 at around 3,100, and our sp CHs come in at around 3,300. So you can have an alkene and an alkyne in an IR, and if you don't have any sp2 or SPCHs, then you won't get a signal. So in other words, if you have a tetrasubstituted double bond that doesn't have any hydrogens on it, then you won't get a signal above 3000 for that functional group. If you have a disubstituted alkyne with no hydrogens on it, then you won't get a signal at 3300 for that functional group because there's no SPCH here or there's no sp2CH here. Another functional group that gives us a signal in IR is a carbonyl. So a C double bond O gives us a signal at around 1700, and that signal is going to be a very strong signal coming almost to the bottom of the spectrum. Okay, so a ketone comes in at around 1720. That's a specific type of carbonyl. But if that ketone is conjugated, in other words, if we can draw a resonance structure for that species, okay, then remember we can draw this resonance structure for a ketone. Okay, it's going to give us an O minus and a positive charge here. Then that's going to lower the energy of that system because that resonance structure exists, and the ketone will have a lower frequency for it will absorb in a lower frequency. Okay, and that's because we can draw these resonance structures. So for a ketone we only have one resonance structure, but for the conjugated ketone we have three possible resonance structures. So having more resonance structures gives that species a lower energy, and because resonance structures stabilize the system. Okay, and the same thing is true with esters. Esters show up at around 1740, okay, if they're not conjugated, but if they're conjugated, they're going to come in around 1710 because they have more resonance structures available. Intensity is another feature that we need to consider in IR. A strong signal is going to come all the way to the bottom almost of a spectrum, so that's like a carbonyl, can be very strong. A weak signal is going to be more toward the top, so it doesn't absorb as much, and that'll be characteristic of an asymmetric carbon-carbon bond, for example. And this is due to a difference in electronegativity between the two atoms, or a strong change in dipole when that bond stretches. So if a strong change in dipole is initiated by the stretching of that bond, then we'll get a stronger signal. So the difference between, say, a carbon-oxygen bond, it's going to have a stronger change in dipole when it absorbs than, say, a carbon-carbon double bond. That's going to absorb less strongly because of the difference in dipole. Okay, there's not as large a difference between a carbon-carbon bond versus a carbon-carbon double bond versus a carbon-oxygen double bond. So here we have a strong signal for the carbonyl and a weak signal for the carbon-carbon double bond. Now if we have a completely symmetrical carbon-carbon double bond, then we don't see this carbon-carbon stretch in IR because no change in dipole is initiated by the absorption of radiation. In other words, it doesn't absorb there because we don't get a change in dipole in that region. Okay, so if that's for something that's symmetrically substituted, a symmetrically substituted alkene like we have here. Also, intensity can be affected by concentration or by having multiple bonds of the same type vibrating. So if we have a whole lot of sp3 hybridized CHs, you're going to have a stronger signal just below 3000 versus if you only have a few of that type of bond, then you'll have a weaker signal. So even though CH bonds are not very polar, you can usually get a very strong signal just below 3000 because there are often many of them in an organic compound. Okay, and this feature is actually used in the Intoxilyzer 5000 that determines blood alcohol levels used by police officers. So a higher concentration of bonds in the sample is going to indicate that you have a higher alcohol level. Okay, so if you have a stronger signal strength, it indicates you have a higher concentration of alcohol. So some signals can be broad while others are narrow. Most signals are broad unless hydrogen bonding is a factor. So we usually see the broad signals for like NH, OH bonds or carboxylic acid bonds, and we'll see narrower signals for things like the carbonyl that doesn't have hydrogen bonding. So OH bonds are OH bonds form hydrogen bonds, and that weakens the OH bond strength, and that causes broadening of the signal. So let's look at some examples of that. So here we have the OH that's actually participating in hydrogen bonding. Because it has a lot of different modes of stretching vibrations, that broadens the signal out because it's hydrogen bonding with a lot of neighboring molecules. Sometimes if you have a less polar solvent, you could even see a free OH in the spectrum at around like 3600 or so. And that's coming from an OH that isn't hydrogen bonding, so that's going to give you a narrow signal. Carboxylic acids, look at this. This is our 3000 mark here, and generally we look just below 3000 for our sp3 CHs, but a carboxylic acid is so broad that it even extends beyond the 3000 region over to the right of it. And so carboxylic acids are very broad because they have not just hydrogen bonding, but they form dimers. So in this spectrum, we'll see the carboxylic acid OH and the carbonyl from the carboxylic acid. Remember, a carboxylic acid looks like this. So the OH signal is here, and the carbonyl signal is at around 1700. So dimerization occurs in solution, and that's what causes the broadening of this carboxylic acid signal. Another thing to note about carboxylic acids is if you have a solid carboxylic acid, the signal will often be kind of jagged. Primary and secondary amines exhibit NH stretching signals, where the primary amine, so a primary amine has two hydrogens, okay, and one R group, and these two hydrogens can either stretch symmetrically or asymmetrically, whether they're either going in the same direction or in opposite directions. So they have two stretching modes, so that's going to give them two signals. But you can just think of it as though if you have two hydrogens in IR, you get two signals. If you have two hydrogens on the nitrogen, you get two signals. Secondary amines have only one nitrogen-hydrogen bond, therefore only one stretching vibration, and that's going to give you one signal. Okay, and tertiary amines, where if you had three things connected to your nitrogen, you're not going to get a signal in IR. So we're going to look at some of those. So here we have a primary amine on the left. It has two hydrogens attached to the nitrogen, so we get two signals in the IR, and these are usually kind of broad. On the right, we see a secondary amine, so it has one hydrogen, and therefore gives us one peak in the IR. And again, tertiary amines don't give us a signal in IR for that nitrogen-hydrogen bond, so they're just not useful. IR is not a useful technique for a tertiary amine. And again, this is because if you have two hydrogens on that nitrogen, they can either be stretching in the same direction, or they can be stretching in opposite directions. So symmetrical stretching or asymmetric stretching. Okay, and so that's going to give you two signals in the IR, or two peaks for a primary amine. Okay, so again, in this region, 1600 to 1850, we're going to check for carbon-carbon double bonds or carbon-nitrogen double bonds. 2100 to 2300, we're checking for triple bonds. 2700 to 4000, we're checking for bonds to hydrogen. And we analyze the wave number, intensity, and shape for each signal. Okay. So the first thing you do if you start looking at an IR spectrum, and notice here that this spectrum's been cut off at around 2600, so it's not an entire spectrum. This is a snapshot, okay, or an inset of a spectrum. So just below 3000, we generally see sp3 CH stretching. Okay, above 3000, we have at around 3100, we can have SP CH stretching. At around 3300, we have, I'm sorry, this was sp2 CH stretching. At around 3300, we have SP CH stretch. Okay, also at around 3300, we have the amines. So for a primary amine, that's going to be 2 signals. And then at around 3300, we also have an OH, which is going to be broad. Okay. So IR can help us distinguish between two compounds. So for example, if you're trying to run a reaction and you're starting with an alcohol and you convert that to a ketone, you can run IR as you move along to check the progress of your reaction, just like you do with TLC. So for your starting material here, we're going to have an alcohol that's going to give us a broad peak at around 3300 for that OH group. And just below 3000, we're going to see our sp3 CHs. So those will be the main peaks we'll have in this spectrum. And then as we do the reaction, which is an oxidation, for the molecule on the right, just below 3000, we're going to have sp3 CH stretching. Okay. And then we won't have anything above 3000, but then at 1700 we're going to have a sharp peak for that carbonyl. Kind of ran out of space here so you can't see it very well. We're going to have a sharp, strong peak for the carbonyl at around 1700. So for each of the following compounds, determine whether or not you would expect its IR spectrum to exhibit a signal to the left of 3000. In other words, do we have a carbon-hydrogen bond that's from an sp2 or spCH? Okay. So here, this molecule has an sp2CH, so we're going to get a peak at around 3100 for that. This molecule has no sp2 or spCH. This molecule does not have an spCH because it's di-substituted, so we'll not get a peak above 3000 for that one. And this molecule has an sp2CH, so we're going to see that peak at around 3100. So each of these compounds contains 2 carbonyls. Identify which group will exhibit a signal at a lower wave number. The carbonyl here on the left is isolated, and therefore it will it's not conjugated, so it's going to have a higher wave number. It's going to be about 1700, 1720. And then we have a conjugated carbonyl here that's going to come in at maybe 1680. Okay, the next molecule has 2 ester functionalities. The one on the right is isolated, it's not conjugated, so that's going to be around 1740. And the one on the left is conjugated, so it may come in around 1680, 1720, something like that. So the one on the left is going to be a lower wave number. Okay. The question here was, which of these is going to give us a stronger signal? Well, we're going to have a larger change in dipole in the molecule on the right, so the molecule on the right is going to give us a stronger signal. Okay. Now the next question is, match each compound with the appropriate IR spectrum. Okay, so what features do we see in this spectrum? If we draw a line at 3000, just below 3000 we have the sp3 CH stretch. Just above 3000 we have a weak peak there. Okay, and then everything else is pretty much in the fingerprint region except for this peak right here. So what do we normally see about 1600? We see carbon-carbon double bonds. So what about 3100? We see the sp2 CHs. Okay, so what does this correspond with? It corresponds with an alkene, an asymmetrically substituted alkene. Let's match the next spectrum with its appropriate compound. So we have a peak at around 1700 that's obviously from a carbonyl. And so which molecules have carbonyls? Well, we have a carboxylic acid and we have an ester. We also have this peak here at around 1100 that could be from our carbon-oxygen single bond, though it's hard to tell in IR because of it's in the fingerprint region, right? So this is probably our ester right here because we don't have the carboxylic acid OH. That would be incorrect because there would be a peak over here if we had a carboxylic acid, a big broad peak. Alright, the next spectrum doesn't have a whole lot of interesting features. Just below 3000 we have our sp3 CH stretch, okay? And then everything else is below 1500, so this is obviously an alkane. Our alkane is here. The next molecule, here's our 3000 line. Just below 3000 we have the sp3 CH stretch. At 3300 we obviously have some kind of an OH peak here. And so let's look at our compounds. We have OH here and OH here, right? But this is not the carboxylic acid, because if it were we would have a strong peak at around 1700. So this must be our alcohol. Alright, the next molecule has a very broad OH peak that extends beyond 3000 above and below, and it has a large peak at around 1700. So this is our carboxylic acid. The next spectrum has a broad peak at around 3300, and this one actually has two peaks on it. Notice those two small peaks. So this is our amine. Let's describe how IR can be used to monitor the progress of this reaction. This is an oxidation reaction. We're going from an OH to a carboxylic acid. So if we look at, say, 400 to 4000 here, this molecule just below 3000 would have sp3 CH stretching. At about 3300 we'd have an OH peak for the molecule on the left. The molecule on the right is also going to have, let's draw our dividing line at 3000, sp3CH just below 3000. It's going to have then a very broad OH peak for that carboxylic acid OH, and then at 1700 we're going to have a peak for the carbonyl. So comparing the left to the right, the OH peak will get broader, and the carbonyl peak will show up. So we wouldn't have that carbonyl in the spectrum for the molecule on the left. To monitor the progress of this reaction, where we're going from a triple bond to a double bond, okay? So this triple bond on the left is not going to have a peak above 3000 because it is not, it doesn't have a CH, it doesn't have a sp hybridized CH. But it is asymmetrically substituted, so and we do have some sp3 hybridized CHs, so just below 3000 we'll see our sp3 CHs, okay, and obviously we're going to have a carbonyl at 1700, but that's going to be in both of them, okay. But around 2200 we're going to have this carbon-carbon triple bond peak for an asymmetrically substituted carbon-carbon triple bond. Okay, that's going to be our carbon-carbon triple bond. Carbonyl at 1700. So for the molecule on the right, we've got our sp3 CHs just below 3000, and then we've got these sp2 CHs that showed up in this molecule. So at around 3100 we're going to have an sp2 CH stretch. We're still going to have that peak at 1700 for the carbonyl, but now our peak for the triple bond has moved to about 1600 for our carbon-carbon double bond, our asymmetric carbon-carbon double bond. So those will be the differences in these spectra. Here's an example of another reaction that we can do, and this one's going to be very similar. The main difference is here. This is a symmetrically substituted carbon-carbon triple bond, so we'll have no signal at 2200 for that carbon-carbon triple bond. We'll also have no signal at 3300 for the carbon-carbon for the carbon-hydrogen sp hybridized carbon-hydrogen bond. Okay, so this molecule is just going to give us a peak at 1700 for the carbonyl and an sp3 CH peak just below 3000. When we do this reduction here, now we have these CHs, but we're still symmetrically substituted. So we're not going to get a peak at 1600 for that carbon-carbon double bond, but we're going to have a peak at around 3100 show up for the sp2 CHs now. Alright, now here's a different reaction. We're just reducing this double bond here. We didn't have any hydrogens on that double bond, so we had no peak at 3100, but it's asymmetrically substituted, so we would have a carbon-carbon triple bond peak at 1600. That's going to go away, so we're going to lose that carbon-carbon triple bond peak at 1600 going from left to right. Okay, so that concludes our discussion of IR for Klein organic chemistry. Now I have another video discussing interpreting IR that I think is much more useful for understanding how to interpret peaks in a spectrum. So go watch that video if this video was confusing to you, and I think it'll become more clear. Thanks for watching, and I'll see you next time.